Welcome everyone to the third installment of PyDataTT, the local chapter of the NumFocus PyData group. We're very excited for you all to meet our next speaker, who is Rajeev Ratan. But before that, just a quick mention of the code of conduct. So be kind to others. Do not insult or put anyone else down. Be professional at all times. All communications should be appropriate for a professional audience, and harassment of any form, shape, or size will not be tolerated. PyDataTT is a welcoming and friendly community, and we look forward to your current and future participation. So with that, let me introduce Rajeev Ratan, who is going to be talking about license plate recognition in Trinidad and Tobago. Lots of interesting stuff. So Rajeev, take it away.
Thanks, Greg. All right, let me just share my screen with you guys. Okay, you guys seeing my screen now? Cool. Okay, so welcome to my presentation on performing and evaluating license plate recognition on license plates belonging to Trinidad and Tobago. So this is just a quick preview of what you'll be seeing and how I made this system, basically. So let's begin. So a bit about myself. I'm a data scientist, but I studied electrical and computer engineering back at UE in 2006. Did my master's in artificial intelligence in the University of Edinburgh 5 years ago. And since then, I've been working as a data scientist in London for about 3-4 years. And then for the last year and a half in Trinidad for various companies, and then doing research with TT Lab as well. My research interests are mainly in computer vision, deep learning, general data science, now getting into algorithmic trading, which is pretty fun. And I have one publication, but I have a couple that might be out soon sometime this year, hopefully. So this is just a quick preview of what I'm demoing here today. So as you can see, there's a live video, well, not live, it's a pre-recorded video with it recognizing license plates on these cars that are passing on this road by St. James here. So it works pretty well. You can see it's getting mostly all the license plates, and it's stationary. It's like locking onto them and moving along with the cars. So it's working quite well. So this is just a quick outline of this presentation. So I won't read through these slides. I just ask for you to browse and see the overview. So firstly, why detect license plates? Well, you can do an automated parking entry system with a visual recognition based license plate system like this. Or law enforcement can use it if they have it on enough CCTVs, can quickly find vehicles if you're trying to find a criminal or someone escaping, which would be a criminal actually. You can do fraud detection with people who have fake or duplicate plates. You can track vehicles from camera to camera as well using the license plate. You can even do some cool data collection, like if you want to see how many registered taxis, because we have specific plates for taxis in Trinidad, H plates. So you can use that, or you can track rental plates or different types of things. Or you can use it for automated toll systems as well. So ALPR, automatic license plate reading, is easy, right? Well, technically, no, it's not. It's quite hard to do it right. Because in real life, images are dirty, skewed, poorly lit, blurry, noisy, low resolution, and they have a lot of other issues too, which you'll see in upcoming slides. And right now, even the best commercial systems score between 70-75% accuracy on this real-world camera data, which is good, but not good enough. And some of the top state-of-the-art solutions right now have been checking out score upwards of 85% on their test data. I don't know if that's on real-world camera data. That's just what they use for their test sets. But even then, you still require like expensive GPUs because they're running pretty deep CNNs and other detector networks to get this accuracy. So these are some examples of plates that are hard to read. You can see a host of issues here. But generally, even a human can't really read these plates too well, unless like I can read this one and this one, but the others are quite hard to read. So as I said, low quality images. These were images taken from a CCTV camera, and you can see that even though it's fairly legible to us, like in this one, it's hard to tell whether this is a bee or, well, actually, I think it's a B, but it could also be a O or D. This one is a bit smudged. This one, it's the 8s and 9s are kind of hard to identify. This one is fairly readable. It's just a little pixelated, and so are these as well. Now, there are also non-standard fonts. Now, this isn't actually a font. This is just a license plate that actually faded over time for some reason. But I've seen a couple of plates like this on the roads right now, where maybe because of sun exposure or some damage or some low quality license plate, it begins changing and kind of warping the fonts a bit. Also, at nighttime, there will be illumination challenges. You'll have issues where you get like maybe some overexposure here and here, or maybe it's just generally a little hard to read because of nighttime. Different cameras, so different light sources can affect how the plates look to the camera. Also in daytime, you have some illumination challenges too. Like you'll have some harsh shadows like this, or maybe it's reflecting on the sun too much. This one is fine, but generally I've seen a couple of times where the sun was reflecting directly off the plate and sort of like overexposing it, totally like blurring it out what it would have been. So there's like a shadow here, but it's not too bad. Dim lighting is another issue too. At dusk, before people turn on their park lights, it's probably going to be a bit dark and hard to read with even with a naked eye. And then you have some damage or obfuscated plates. These aren't too bad, just the best examples I could have found on my image data set. You have things like the toe bar stuff blocking some of the letters. This plate is bent. These have screws over the letters. This one has a bumper on it. So you can generally see there are sometimes obstructions over the plate. And then they have non-standard locations or just odd vehicles. So if you have a detector and the data set only has plates like where you expect to find them, like in this car, if the plate is up here, that can present a problem, like in this tractor here and this motorcycle here, or this bus. Well, it's actually a food truck that it was on the left here. So for this van and this car. And then when you're taking into consideration CCTV positions, they're not always going to be, well, most times they're not positioned quite well. They're going to be at an angle toward the road, and you're going to get either like some very weird angles like this, or this is like a more common angle you'd probably see from a CCTV that's positioned like on the side of a road. These kind of like skewed plates are common, and these skewed plates are where most standard license plate recognition systems fail right now. Also rain, or lastly, rain is another problem that is going to cause some blurring of the license plate. So our goal was to create an efficient and accurate detection system of license plates, basically based on poor quality CCTV images, or at least I can deal with those poor quality CCTV images and do it in an efficient manner so that it can be deployed on an embedded system and attain an accuracy of at least upwards of 80% on plate accuracy. So right now, there are a few off-the-shelf solutions. This one, Plate Recognizer, which is quite popular. It works fairly well. It's not programmed for Trinidad license plates, although Malaysian license plates, I believe, are quite similar to ours, and I used the Malaysian model, and it doesn't always work too well. A lot of times I would actually have issues with numbers or letters being mixed up. Like it might interpret a 0 as an O and vice versa. So if they kind of had Trinidad plates system maybe pre-programmed there, it could help. But as of now, it doesn't work too well. These are some of the latest research papers I found on license plate recognition. A lot of people are getting quite good results on detection, which is easy. Well, the easier part of it. Accuracy on plate accuracy, meaning that even if you get one character wrong, that counts as the plate being inaccurate. So that's why plate accuracy is 78%, 78%, 76% here. So it's never quite good because just one character throws off the plate accuracy, whereas character level accuracy is usually quite high, because even if you get one wrong, that's 7 out of 8 digits correct usually. So overall, your character accuracy will always be higher. So this one has got 98%, which is quite good. So some of the current limitations of traditional OCR methods, like I mentioned, would be plates like this. I mean, to be fair, I don't think anyone can even read this plate. Skewed plates with a high degree of rotation as well present a lot of problems. Images with lack of contrast like this also present a lot of problems to those existing systems. So I think all of us here are Trinis, but just to go over what Trini plates or Trinidad and Tobago plates, how are they kind of like defined? We have single and two-line plates, which are allowed legally. We can use both black and white backgrounds, but no other colors are allowed. Even though there's a standard font, I do see a lot of small differences in the fonts throughout plates, and sometimes some of them are quite narrow. So the kerning, that's the distance between characters, makes it a little bit difficult to read if it's a low quality image. Then we have some of these non-standard plates, which are Defense Force and Coast Guard plates. Also, we have no I, Q, or V characters in our plates because they can be confused with other letters, which is a good thing. Very progressive thought from years ago. But also, we have a class imbalance with our plates because everybody, like 99% of plates, well, maybe not 99, but 80% of plates are P plates. And then T plates are quite popular. It's trucks. H is not that common because we don't have that many registered taxis. And rental plates are very rare. You might get like 1 out of every 200 might be a rental plate, at least in our data set. That's what that was the occurrence or the frequency. So this is an overview of the system that we designed. So let's quickly go over it here. So imagine this is a video here. Only use 3 images here, but you'd probably get like maybe about 30, 40 images in a video that of this car driving here. So we have our license plate detector, which you saw in the beginning, how it works. So imagine if every license plate image it captures, we crop it out of it. And so we have like this group of, say, 30 plates. So what we do, we have an algorithm that auto-selects the sharpest plates. So we don't take all the plates because there's no point in taking a blurry plate like this. So we get maybe the top 10 sharpest plates here. And then what we do, we just have some minor pre-processing on those plates just to sharpen, decrease the noise, increase contrast, and do some automatic de-skewing. So we go from this top one here to this bottom one here. So you can see it's not like a drastic difference, but it is slightly cleaned up. So we do that for all the plates in the pool here. And then what we do, we take the OCR reader, which we built separately, and we run it on all those plates here, all these like, let's say 30 plates. Oh, sorry, 10 plates that were selected from that batch. And we do the OCR grammar reader decoding. So we get all the characters out of those plates. And we do a temporal redundancy, which basically is a majority vote. So if PDW1182 was the most common OCR read output from all of the 10 plates we identified, then we go with this. So we do it down to this temporal redundancy majority vote to get the most frequent occurrence, because even if, as you may have noticed, hopefully in the video, it doesn't always capture the full plate with this detector. Sometimes little pieces can be missing, and that's going to affect the OCR reader. So hopefully, if we get at least 10 good images and 9 of those images give us the same answer, we obviously know it is most likely PDW1182. So that's basically an overview of how our system works. So now let's dive into our detector. So I just blew this plate because this is in a private area here. But anyhow, so what's the difference between classification and localization? So classification means whether you're, in computer vision terms, classification tells you whether an object is present or not in the image. So if you pass this image to a license plate classifier, it's going to say license plate present, but it's not going to tell you where the license plate is. That's how classification models work. However, if you use an object detection model, an object detection model will actually draw a box around the plate like this and tell you the bounding box or coordinates of the object in the image. So object detectors are more sophisticated, but a lot harder to build. So what we did, we used the YOLO 4, which is currently probably the second best object detection model out right now. Efficient det here is perhaps better because you can see it has a higher accuracy score here. but it is a lot slower and more computationally expensive than YOLO 4, which is what we use in this demo. So YOLO 4 has already been pre-trained on 80 object classes from the MS COCO object detection data set. This is a common object occurrence data set, and it automatically recognizes 80 different classes, as you can see some example classes here of how it works. So these are some alternative object detectors with SSDs, RFCNN, fast RFCNNs, EfficientDet, and Detectron 2, which is also quite good. However, we still went with YOLO because YOLO probably has the best performance to computational intensity, computational requirements. So again, it gives you a very good frame rate and very good accuracy at the same time, which is a good balance, which is what we would want ideally. So a bit about how YOLO works. I wouldn't spend too much time on this, but YOLO basically what it does, it divides the image into an S by S, or typically a 7 by 7 grid, although we can configure this differently. And for each grid, it proposes a number of boundary boxes. So this is the example of a boundary box it's proposing here. And then it makes 2 boundary box predictions per cell to basically, it kind of extends outside of the cell for it to be for the object that it's trying to detect. So it's a little more in depth now with YOLO. So for each grid, we have the boundary box proposals here, like these blue boxes right here. And we have box confidence scores and these parameters here, which is basically the coordinates and the box confidence score. So the box confidence score represents how likely that the image or the category of class, which is a license plate, how it represents how confident it is that it's in the box. So it only actually detects one object per grid, which is, in our case, that's fine because we just trained a detector to detect one object. But you can train YOLO, as I showed you before. YOLO is trained on 80 different classes. The default YOLO model, the pre-trained one. But what we're doing, we're basically applying transfer learning to that. So we're using those pre-trained weights and training it now to detect license plates. So just moving on here, this is the class, the C class probability, conditional class probabilities for the object being here. So it will actually propose what most likely object is on each box. And then it uses non-maximum suppression, which is a way to reduce overlapping box proposals that you can kind of see here. So again, it is an algorithm that we use to get the best box. So now moving on, this is the YOLO 4 architecture. It's quite deep. It's 161 layers or 67 layers, 167 layers, not entirely sure. This YOLO version 4 uses the CSP darknet backbone, which is probably, they have 3 different backbones they tried in the paper. The CSP darknet 53 backbone was the one that gave the best performance. Actually, there was one that gave better performance, but it was a bit slower. So the authors went with this one. It is a variation of DenseNet. And it performs quite well after they tried it. So when we're training a YOLO 4 model, we have 3 different losses that it tries to minimize. There's a classification loss. So if an object is detected, it is a square error loss of the class conditional probabilities for each class. Also, there's a localization loss, which measures the error from the predicted boundary of the box to the ground truth. So you could already see these 2 making sense. And then there's a confidence loss, the confidence that the object lies in the box. So those are the 3 loss functions it's trying to minimize while we train YOLO 4. So this is now how we created our data set. So we used this Python program called label image. Basically, it's quite a nice GUI program where you just draw the bounding box over the license plate, and you can save it in either the darknet YOLO format or the Pascal Fox format as well. So this is the output for each image. If there were multiple license plates in an image, you would just have another line with the coordinates of the bounding box here. And what we did, we trained it on 80% of our labeled image data set. And we have 10% being the test and 10% being the validation, which we assessed the performance on afterward. So this was the output of 7 hours of training our YOLO 4 model. After 2000 iterations, we got average precision score, mean average precision score of 89.76%, which is quite good. These are true positives, false positives. The loss was also 0.26, which is quite good. Loss, basically, for those of you who don't know, is like a penalty function that you try to minimize in machine learning. Basically, it is the measure of the correct labels minus the incorrect labels, so classifications. So loss is basically analogous to accuracy in a way, just a penalty function. And the FPS we got on our GPU, which was a Tesla P100, was 54 frames per second, which is quite good. Although we need us to run on a much slower embedded system, which would be the Jetson Nano, which most likely will probably get something like 2 frames a second, which is not fast enough, but we do have a plan for that, which I'll discuss further. So I'm just going to talk a bit about the mean average precision score, the MAP score. So MAP can be quite confusing. So I'm going to introduce you to something called IOU first, which is just the overlap, measure of overlap. So imagine if this red box was what our detector proposed, and this green box was the ground truth. How much percent of the proposed box from our network, our model, overlaps with the ground truth is a measure of is IOU measure. And we usually consider 0.5 to be acceptable, with 1 being ideal. It means it's perfect overlap. So now mean average precision, which is the benchmark you use to measure or assess detector models, would be the I'll explain to you, but I'll go through precision and recall first. So precision is the true positives over true positives plus false positives, which basically means that when your model predicts positive, how often is it right? So you can think about it a bit, but basically if a model is predicting a box like this here, let's assume it's a bit closer to the ground truth box, how often is it right is a measure of precision. And we determine that rightness by this, whatever we set our IU threshold to be. So let's say we set it at 0.5. So anything above 0.5 would be considered correct. And then we have recall, which is true positives over true positives plus false negatives, which measures how well our model is at finding all the positives in our data set. So we basically recall will measure how much we don't want to, how much you want to basically get the false positive, the true positive. So how much, sorry, it's fixing something here. So how good our model is at picking up the positives and not missing the false negatives. Okay, so false negatives would be a missed positive exactly. So now what mean average precision is, or MAP, is basically the area under the precision recall curve. So imagine we're plotting precision here and recall here, and we're varying the IOU threshold from 0.5, let's say we're varying it from 0 to 1. We'll have this area under the curve here. So MAP basically just an average of the average precision at each point, each IOU threshold point. So that's how we measure the mean average precision, and that's how you assess object detectors. So we got 89% there, which is quite good, like I said. So these are some examples of our model performance in the real world. These are all in the test image data set, so it wasn't trained on these images. It never saw these images before, and it picked up the license plates perfectly, even in rain, on all these images here. And now, even on non-standard vehicles like this steamroller, this mini steamroller here, it got it right. Got it right for all these cars in this car park here, and even this ancient antique fan as well. And here's another demo of it working in the real world. So you can see it's picking up most of the plates once it's above a certain size, it'll get it. So again, pretty cool stuff. And it's going to end here shortly. Yep. So now that we are detecting plates fairly accurately, we now have to read plates. So that's this part of this block here. So I wouldn't actually talk about the selecting the sharpest plates and this image processing here that's done to sharpen the plates. Those are fairly basic. What I will talk about is the OCR reading part. So firstly, we try to use Easy OCR, which is a Python, one of the state-of-the-art Python libraries to read characters, and it did not perform well at all. Many times, for some reason, it would completely like not get the digits right. It would like in this one, it thinks a 5 is a G. This one, it thinks this 1 is that character. So you can see it's not doing too well. It did this one actually fairly well though. This one, even though it's correct, this is actually a O, not a 0. Got this one right, but overall it's not great. There's also PyTesseract PyTesseract as well, but PyTesseract actually performed worst. So what I did, I spent some time trying to build my own character segmentation algorithm. And then what you do is once you have the characters here, you can just feed it through a CNN. And this is a quite easy method to read characters or recognize characters. However, it is so tricky to do well because while it performed perfectly on these plates here, plates that are vertical like this with two lines. It was really hard to get it right. Sometimes when there's a border around the license plate, it missed it as well. In this case, it has overlapping characters. So it would have required a lot of manual tweaking to get this right. So rather than continue to develop this algorithm, what we did is that we tried to find a more resilient and stable solution. And that is when I came across something called connectionist temporal classification. So this is an operation that is used to tackle unaligned sequence data. And it's unaligned sequence data is basically like speech data or handwriting data. I'll give you some examples you can see later on in the upcoming slides. But what we did, we posed our character segmentation problem as a sequence labeling problem, and we applied CTC loss to it. So there was a paper on using CTC loss to decode captures like these here. So what I did, I adopted that method, that network design there into our license plate problem. So this helped a lot because we already have our license plates extracted into these little files, like I'll show you shortly after. And they're already labeled. So we don't need to do any character segmentation afterward. And we don't need to separate plates into like single or double line or white background, black background plates. We can just feed this data in, and CTC loss helps us deal with all of those inconsistencies or unaligned problems. So like I said, what makes it so useful is that all we have to do is just present the image like this to plates and the label, which in this case would be PBC 827 and PAC 9735, blah, blah, blah for the other one. There's no need to give the positions of the characters, okay? So this is an example, high-level example of how CTC loss would work. This here is an image taken from a paper where it was introduced, where it was used for voice recognition. So you can see what it does. Remember, think of this here. This is a sound wave right now. And this is a sound wave of someone saying the sound off. So how do you know where each word starts and stops, or each phrase? You don't. But with CTC loss, you can actually get a probability of a word being here or here as well. So you can break up the sounds like this. So the axe or like this. And it kind of like puts it together to get the sound off, which is the ground truth label. So we did the same thing, but instead of using sound, we use images. So what we do, we have the input image here, and we just feed that into CNN, and the CNN we have the label. So the CNN basically breaks it up into different time slices, you could consider it, and feeds it to an RNN. And RNN feeds into the CTC loss function trading operation here. And it tries to predict the probability of a letter at each occurrence here. So for those of you who don't know, CNN stand for convolutional neural networks. These are a type of deep learning networks that learn features or maps or like patterns in an image. So, sorry. So basically you use it to feed an image in and you extract features out of it. And that could be used for classification afterward. So that's what CNNs are. And then also we have RNNs here. RNNs are a type of neural network or deep learning network that takes sequential data as the input. So it actually knows what the previous inputs were, past information, so it uses that to predict the output. So as you can see, if we combine CNN, which is extracting the image features out of an image, with an RNN, it kind of like poses the problem back as a sound wave problem almost. So that's pretty cool. And then this is our network architecture for CNN and then for the RNN, LSTM layer. And then it outputs to the CTC loss layer, which does its magic, basically. So training using the CTC loss takes the output of the RNN and CNN together along with the ground truth labels. And then what it does, it outputs a score, like a matrix score, for a character being at each time step here. So this is how it breaks up a license plate into different time steps. And it tries all possible alignments of the ground truth, and then it gets basically a sum of all the scores. And the score of the ground truth text is high if the sum of the alignment score is high. So it's kind of an example here with the capture model, how it works. So you can see the first one being 3. That's the highest probability of this character here. Then you have a lot of blanks. Now, CTC is notorious for producing a lot of blank spaces characters, which is okay because that blank is a category here. So we just remove that afterward. So decoding, as I was explaining previously, this is just A and B, but you can see we have 5 time steps here. And CTC basically, what it does, it basically tries to find the best path decoding, which basically consists of 2 steps. It calculates the best path by taking the most likely character per time step here, and then undoes the encoding by first removing duplicate characters, because as you can imagine, T1 and T2 would probably produce an A, hopefully, in this example right here. So we have to do something to remove these duplicate characters, which CTC kind of does built into it in a way. There's a lot more to this algorithm. I'm just kind of like talking about it on a high level right now. So now let's talk about our data set. So we trained our OCR data set here on almost 5,000 license plate images that look like this here. These were cropped out of the images in our data set. And we have the labels right here below it. The file name is the label. So it was 33 different character classes here. So you can see the distribution. So as you can see, as I mentioned, in Trinidad, P plates are by far the most common, which is why we have the most Ps. D and C as well, because vehicles in the last maybe 15 years would be PD or PC something. That's how our license plates are standardized at like. And then the next 4 digits in a license plate would be numbers. So that's why numbers are quite common here. With the exception of 0, all numbers are fairly even in this class. And then you have T, B, and then all the little letters here, with O being the least popular. So we may need to collect more O plate data. So our model performance. So after training for 74 epochs on approximately just over 2 hours on an NVIDIA Tesla P100, we got a loss of 1.45, which is okay. Our character level accuracy was 95%, and our plate accuracy was 78%, and the inference time per plate is 0.04 seconds, which is quite good. So these are some examples of plates it got right. We can just look at a handful here. You can see in this one, PCR 4518, which is a blurry one, it got it right. You can see in this one as well, not a blurry one. It got this one perfectly right too. This one is kind of slanted and it got it right as well. So it's doing quite well. However, it doesn't always do too well, because in this one here, which is also slanted, this one here is also slanted. It didn't get it correct. It thought it was PBS 997. So for some reason, kind of merged these 2 2s into 7, most likely because of the slant in it. These are the ones that got wrong. This one is exceptionally hard. So it's okay. We can kind of forgive it. So is this one. But these others are pretty clear and I got it wrong. So upon investigation, I realized that anything with slight skew like this would cause some issues sometimes. White background plates, since they're less in the data set, do cause some issues at times, as well as plates with only two numbers, because maybe it's trying to predict probable characters that aren't there in the blank spaces. So now, when we combine the plate detection with OCR, these are some examples of images I tried, and it actually got all of these right, which is quite good. Even though they're not super hard, it's still, these two on the other end were fairly hard, and I got them perfectly right. So as I said, I was discussing the performance issues, blurred images, skewed images, two-line plates. I actually mentioned white background plates, but I didn't put it here. Plates with less than 4 numbers, class imbalances, which are like R plates, like the rental vehicle plates, or PA type plates, which were less common in the data set. It tend to get those wrongs sometimes. So our plans for improving accuracy would be to collect a lot more data, maybe double the data we have. I still have maybe about 1,000 images we collected over the last month or so to label. We also need to fix the imbalance issues, so collect more taxi H plates, more rental car plates, maybe do some more pre-processing on images just to make it a little clearer, although that part is sort of already taken care of. We can also augment the image data set with some image alterations, like introduce some noise, some skew into the data set. We can even use GANs to generate more images too, or perhaps use SRGAN, which would be computationally expensive though, but we can do that to improve the image quality before feeding it in to our CTC OCR reader. So the future work now would just be to integrate everything together on video, because right now it's integrated for, I would say, only for images, not fully for videos just yet because of some issues with OpenCV4 not supporting YOLO 4 just yet. Hopefully, it should be done soon. I want to try maybe some more different detectors like Detectron 2 or EfficientDet or MobileNet SSD, although maybe not this one. I'll probably just go with these two. What I'll do, I'll also sign up for Plate Recognizer and try the API and compare performance properly against them. And then we want to deploy this on a Jetson Nano. So to do that, we will have to probably use a different version of YOLO version 4, which is called Tiny YOLO version 4, which is almost 3 times, let's say at least twice as fast. So perhaps on the Jetson Nano, we can be getting maybe upwards of 4 frames a second, which it would be good enough for real-time detection. So these are some references here in case you want to take a look at them. Acknowledgements. I want to thank Kevin Ali for helping collecting almost like 80% of our data, Shiva, Resho, and Nydia, and Carissa for providing pics, as well as Professor Patrick Hussein. So that concludes the presentation. Hope it was informative, and I hope I didn't go through it too fast. But now if you have any questions, just let me know.